Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem finding the diameter of a binary tree from the Freaka tree series. So let's assume this is the first binary tree, right? And if I ask you what is the definition of diameter? Now this can be called as the longest path. Yes, I can call the diameter as the longest path between any two nodes, right? That's the definition of diameter. And also this path does not need to pass, like it can pass through the root or it cannot, does not need to pass via root. So if you can understand these 2 points, you can understand the definition of diameter of a binary tree. Like for this tree 1, if I ask you what's the diameter of binary tree, I'll say the diameter of binary tree, this binary tree is 3, and I can say that if you start from the node 4 or node 5, you can take any one. That's the path, that's the length 1, that's the length 2, that's the length 3. So basically if I consider this node 4 and node 3, I can get a diameter of diameter 3. So over here you can see that the path is passing through the node 1, but we have been said that the path does not need to pass via root. Like it can pass or it cannot. Like it's not mandatory that it should pass via node. So if I take this binary tree 2 for an example, in that case if I take this node 6, if I take this node 9, then this is path 1, path 2, path 3, path 4, 5, 6. So I can say for this second binary tree, the distance, yes, the distance from this node to the other node is nothing but 6. I hope you have understood this. And this is not necessarily passing via root. So this is the question that we need to solve. So the naive way is very simple. I can say I can traverse in the entire tree, and if I'm standing at this node, what I can do is I can simply find the longest path passing via this node 1 can be called as the left height of the tree, like whatever is the left height plus the right height of the tree. So for this the left height is 1, so that's 1. For this the right height is 1 plus 1, 2, 3, 4, so that's 4. So I can say that for this the maximum, like if the path passes via 1, the maximum is 5, right? So if I go over here, I can see that we don't have anything here, we don't have anything here. For this guy the maximum I can say is 0 because I don't have any path. If I stand at 3, I can say it's 1, 2, 3, that's the left height. And if I talk about the right height, that's 1, 2, 3. So again 3 plus 3, and that makes it 6. Similarly, if I stand over here, I can say that the maximum height, like in this case, will be 2 plus 0. That's 2. In this case, will be 1. It's 1, 2, 3. That's the left height. And if I talk about the right height, that's 1, 2, 3. So again, 3 plus 3, and that makes it 6. Similarly, if I stand over here, I can say that the maximum height, like in this case, will be 2 plus 0. That's 2. In this case, will be 1 plus 0. That's 1. In this case, will be 0. Over here, like the maximum path, if I call, then it will be 0 plus 2. So that's going to be 2. Over here, it's going to be 0 plus 1. That's 1. Over here, it's going to be 0 plus 0. That's going to be 0. So what I can say is, for any given node, if I can figure out what's the left height, what's the right height, if I can add them up to get left height plus right height, that's going to be the length of the longest path passing via the given node. And if we are given n nodes, so if we can find LH plus RH across every given node, can I say the maximum of left height plus right height is what is going to be my diameter of any given binary tree? Indeed, we can. So if I talk about the brute force, it's very simple. We're going to do a traversal, recursive traversal, right? And what I can say is, if I am doing a recursive traversal starting from the node, which is going to be the root of the tree, what I can do is, we can definitely go to the left, and that's a simple recursive traversal. Every time just go to the left and go to the right. So that's how you generally traverse the entire tree. So every time you are at any given node, just make sure you get the left height. Again, very simple. If you're standing over here, go to left, go to left, go to left, and count like till the leaf node, go till the leaf node. So in that way, you can easily find the left height of the binary tree. Similarly, in order to find the right height, go right, go right. If there is no right, then go left, then go right, go to the leaf node, right? Once you've gone to the leaf node, you can easily find the right height also. Over here, you can also find the left height. And if you don't know this, I've already done this in one of the previous questions. You can definitely watch out that video. So you can find the left height and right height. So once you've figured that out, you know, you can have a variable like maxi, and you can use that maxi variable, like that can be globally declared, or you can pass a reference or a pointer to it. Like that's your choice. You can have this globally declared. And what you can do is every time you have a left height and a right height, just add them up. Because for every node, you have LH and RH. Just add them up. And for every node, compare that with maximum. So ultimately at the end, when you have traversed left, right, that means you have traversed the entire tree, your maximum, yes, your maximum is going to store the height of the given binary tree. Now you might be thinking, but Striver, this is big of n square. I'll be like, yes, this is indeed big of n square. Why? Because store the go tree. Indeed, we can. So if I talk about the brute force, it's very simple. We're going to do a traversal, recursive traversal, right? And what I can say is, if I'm doing a recursive traversal starting from the node, which is going to be the root of the tree, what I can do is, we can definitely go to the left, and that's a simple recursive traversal. Every time just go to the left and go to the right. So that's how you generally traverse the entire tree. So every time you are at any given node, just make sure you get the left height. Again, very simple. If you're standing over here, go to left, go to left, go to left, and count like till the leaf node, go to the leaf node. So in that way, you can easily find the left height of the binary tree. Similarly, in order to find the right height, go right, go right. If there is no right, then go left, then go right. Go to the leaf node, right? Once you've gone to the leaf node, you can easily find the right height also. Over here, you can also find the left height. And if you don't know this, I've already done this in one of the previous questions. You can definitely watch out that video. So you can find the left height and right height. So once you figure that out, you can have a variable like maxi, and you can use that maxi variable, like that can be globally declared, or you can pass a reference or a pointer to it. Like that's your choice. You can have this globally declared. And what you can do is every time you have a left height and a right height, just add them up. Because for every node, you have LH and RH. Just add them up. And for every node, compare that with maximum. So ultimately at the end, when you've traversed left, right, that means you've traversed the entire tree, your maximum, yes, your maximum is going to store the height of the given binary tree. Now you might be thinking, but Striver, this is big of n square. I'll be like, yes, this is indeed big of n square. Why? Because whenever you do a traversal like this of left and right, the complexity in order to traverse the entire tree is already big of n, and then you're using a function to figure out left height, which is definitely going to traverse this entire distance of the entire left height, and again you're using a right height, which is again going to traverse. Just imagine you have a tree like this, a skew tree. So if it's a skew tree, you're going to traverse right from the start till the end. So in order to compute the find height, you'll end up taking a big O of n time, which will make this brute force to be big of n square, which is definitely not acceptable. So what we will do is, we will try to optimize this into a big O of n solution. So let's check that out. So in order to understand the big O of n traversal, okay, so you need to know how to find the height of the tree. Yes, you need to understand this, like how to find the height of the tree. And I've already made a video on that. So I'll highly recommend you that you should definitely watch out how to find height of a tree in big O of n complexity. So if you haven't watched that out, please pause this video, watch that, and after that come back over. So this is the exact code. Like if I just remove this maxi, like if I just remove this extra variable maxi, this is the exact code in order to find the height of the tree, where we use the formula as 1 plus maximum of either the left height or right height. Again, makes very sense. So can I say at every junction of node, yes, at every junction of node, if I implicate the find height wala code, I always have the left height, I always have the right height. So if I have the left height and right height during finding the height of the tree, do we need to separately find it? And the answer to that will be no, we don't need to. So what we will do is we'll use the same code from find height of the tree, and we will take LH and RH, and we will say maxi to be max of either maxi, comma LH plus RH. So what we did was, instead of having LH and RH like differently, we use the LH and RH that was always computed while finding the height of the binary tree. Simple enough, isn't it? I'll show you a dry run for this. So at first the node is root, so we come across to root. Right after that, this is not null, so we'll go to the node dot left. So we go to node dot left, and yeah, remember this maximum is 0 initially. So we go to the left. The moment we go to the left, again we go to the left. So this time when we go to the left, it's a null. It's a null on the left. So if it's a null, we're going to return a 0. Yes, we're going to return a 0. So this guy returns a 0. So from left, the left height return is 0. Now we come to the right. Again we get a null. So basically come to the right, we get a null. So this guy is going to return a 0. So can I say RH becomes 0? So ultimately LH is 0, RH is 0 for this particular node too. So what will we return? 1 plus maximum of LH and RH. Before that, we have to do this. For this node, LH is 0, RH is 0. So maximum still stays as 0. Now the LH is 0, RH is 0. So 0 comma 0 max is 0. 1 plus 0 is 1. So what we will return is 1. So the LH returns 1. So the left height now returns 1, right? Now it's time to go to the right height. So let's go to the right. Again, we have a 3. We will go to the left. Again, we have a 4. Again, we'll go to the left. We have a 5. Again, we'll go to the left. We have a 9. So this time we have a 9. So we go to the left. We get returned as 0. We go to the right. We get returned as 0. So ultimately, again, we get 0 and 0. So this is 9 as of now. Now this 9 says 0, 0. So 1 plus max of 0, 0. This is going to return something as height as definitely 1. So LH becomes 1. When it goes to right, it finds null. So this is going to return 0. So the LH is 0, the RH is 0. Which one is max? Like LH and RH is 0. So can I say maximum becomes LH plus RH? So LH is 0. LH is 1, RH is 0. So maximum becomes 1, right? Over here we had 5. So we have to go back. So we will go back with the height, right? We will go back with the height. So height is LH is 1, RH is 0. So 1 plus maximum of LH is 1, RH is 0. So it will become 1 plus 1, 2, right? Again we'll come to the right, and this is going to return 0. So this time LH is 0, RH is 0. So LH plus RH with square. I'll be like, yes, this is indeed big of n square. Why? Because whenever you do a traversal like this of left and right, the complexity in order to it's going to be 1 plus max of these 2. So 1 plus max is 2. Height will be 3. So this returns 3. We'll come to the right. We'll come to the right. We'll come to get a 6. And over here you can definitely return the hand. Okay, but that's not possible in Java. That's why I pass an array which is passed by reference. The node just is what is going to be my diameter of any given binary tree in traversal, right? So ultimately, I try to match that come back over to find the height of. So I am doing called as distance, or it cannot be question. That's one. Zero plus of LH, that's 3. Okay, that's because at every step you had an LH and RH generated. So as usual, guys, the left side is the C++ code and the right side is the Java code. So this time I'll be talking about the Java code finally. So we take the root. Okay. Now, since in Java, the variables are not passed by, like, they do not work as reference. So what I did was I created a array, okay, of size 1, and I called the height function. And right after that, it's a similar code that was written over here. And instead, like over here, if you see in the C++ code, I have passed via and, okay, but that's not possible in Java. That's why I passed an array which is passed by reference, and after that I've done it similarly. So that's the just smart trick that I've used. Apart from that, the code remains same as I've discussed. So the time complex everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem, finding the maximum path sum in any given binary tree. Now what is a path? So if you have seen the previous video, a path is nothing but any path, like you start from any node A and you go to the node B. That is what we call as a path. Okay, and in a path, a single node will only appear once. Path is nothing but any path, like you start from any node A and you go to the node B. That is what we call as a path. Okay, and in a path, a single node will only appear once. So I can say if I'm taking the node 15 and 17, then the path will be this. Okay, now you cannot say that I'll go like this and then I'll come back like this. That's the path. No, a path means any node, like over here the path is 15, 27. So every node is appearing once. For an example, I say the path from 15 to 9. So it'll be 15, 20, minus 10, 9. So there will be multiple paths. Like if I consider every node combination, there will be multiple paths, right? So out of all these multiple paths, you have to figure out which path gives you the maximum summation. Like for an example, if I decide to take this yellow path, I will get 15 plus 20. Like what is the first pair of node A and B? Where thing that comes to my mind is possibly trying out every possible pair of node A and B, where A can be anything, B can be any other thing. So if I try out every possible combination of A and B, and out of every possible combination, whichever path is giving me the maximum sum, I can say that is my answer. But again, if I think of that brute force solution, it's complicated, and if there are n nodes, I'm going to try out n square combinations. So I should not go across that path because I'm already seeing that we have an n square, and again we have to figure out the distance between two nodes. It's going to take a bit more time, so we will not go across that path. Instead of that, we'll go across something that we learned in the previous videos, that is finding the maximum height of a binary tree. So if you haven't seen this video, I'll highly recommend that you should definitely check out this video, finding the maximum height of a binary tree, and as well as finding the width of a binary tree. So these two videos are the prerequisites in order to understand the maximum path sum. So please pause this video if you haven't seen this, go and watch that out, and after that come back so that you can understand this in a smooth manner. So can I say, if I am standing at any node, then if I figure out what is the maximum like path at the left, maximum path sum at the left, and if I can figure out what is the maximum path sum at the right, so can I say for this particular node, the answer will be the node value, assuming the node is having a value val. On the left, the max left. On the right, the max r. So can I say this is the formula node, the path at the left, maximum path sum at the left, and if I can figure out what is the maximum path sum at the right. So can I say for this particular node, the answer will be the node value, assuming the node is having a value val. On the left, the max left. On the right, the max r. So can I say this is the formula that I can get for any given node? If I know the maximum sum on the left and maximum sum on the right, then the formula. If I know the maximum sum on the left and maximum sum on the right, then the formula will definitely be val plus max L plus max R. So if for a particular node, I can figure out a formula, can I say if I can apply this formula to this node, 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 then I can actually figure out which is the maximum path across any given node. Like for this node, the maximum path will be this one, right? I can easily figure that out via this formula. For this node, the maximum path will be this. I can again easily figure out via the formula. Now you might ask, what if driver there is a path which goes across 20, but this is the path that is the maximum? Then minus 10 will cover that case. Now, whenever you're having for minus 10 will cover that case. Now, you don't have to worry. So basically what I'll do is, for every node, I will try to have this curved path. Yes, I'll try to have this curved path for every node. And can I say, if I try out every node, and I apply this formula to every node, then the maximum along every node, like whichever is the maximum among all the nodes, will be my maximum path sum. You'll be like, yes, that makes sense. Something similar to what we did in finding the maximum width of a binary tree, right? So this is what my thinking will be. Now I'll just move across with the solution and I'll do a dry run so that you can understand in deep the algorithm. So if you remember the code from finding the maximum height or finding the maximum width, it appeared something like this, where at the end we were returning something like 1 plus max of LH comma RH, and this was done in order to find the maximum height of a binary tree, if you remember. So over here, what I've done is I've tried to figure out a function max path, which if I'm standing in this node, it figures out the maximum. Yes, it's figured out the maximum path either on the left or either on the right, like whichever is the maximum path, that is what I'm returning. So it's very simple. What I'm doing is node sval, and if the left is max, then this left will be the path, and if right is max, then this right will be the path. Standing at a node, I'm saying, does the left path gives you the maximum sum, or does the right path give you the maximum sum? That is what I am basically returning over here. Now you might ask me, but how is this going to help? Now if you remember the formula that I discussed was very simple. The formula was for every node, you have to figure out the left sum, the right sum, and then you can get for this node the answer to be node val plus the summation of right sum plus left sum. So ideally, if I can figure out the left sum via this formula and the right sum via this formula, then I will be eligible to apply this formula on this particular node. Makes sense? Did not understand? Not an issue. Let's do a dry run. Things will become much more clear. Let's do that. Plus the right to find, the formula was for every node, you have to figure out the left sum, the right sum, and then you can get for this node the answer to be node val plus the summation of right sum plus left sum. So ideally, if I can figure out the left sum via this formula and the right sum via this formula, then I will be eligible to apply this formula on this particular node. Makes sense? Did not understand? Not an issue. Let's do a dry run. Things will become much more clear. Let's do that. So guys, just make sure while backtracking. So this is the step which will go in. So while backtracking, just maintain a variable maximum, and you can just have it via reference in C++. And over here, just do maxi equal to max of maxi comma plus did in maxi value that I pass, and I start at the root of the node. And max, that's left sum plus right sum plus nodes val. Just do this. Okay. This will happen. And node dot val 9. So again, apply the formula. Left sum returns a 15. Why? Because it goes to right. On the left, the sum is 15. Again, makes sense because the node is 15. So what I do is left sum, that's 15, plus right sum, that is 7. 15 plus 7, 22, plus the current node 20. If I consider this path, so 15 plus 7 is 22, plus 20 is 42. So I'll update maximum to 7. 15 plus 7, 22. Ultimate from the node 9. So I update my path 0 plus node got to left. Remember, the moment I move to this left, this will see that it is null. So it'll try to return a 0. Perfect. Again, this right will say, why don't you move to right? Because if you're standing at a node, you always move to left, you always move to right. So you move to right, and this is going to return a 0. So ultimately, the left and right have got you 0. So what maximum will get is left sum plus right sum, that's 0 plus node dot val. And node dot val is nothing but 9. So 9 plus 0 plus 0. So I can say this is one of the paths via this node. This is the U path via this node 9. And that's nothing but 9 plus 0 plus 0, 9. So I update my maximum to 9. Perfect. Next, I will come across and I'll return node dot val, that's 9. Plus max of left comma right. So left is 0, right is 0. So I return only 9. Perfect. I'm going to return only 9. So this minus 10, when you're standing from the left, yes, from the left, it got a minus 9. So left sum is minus 9. It's time to go to the right sum. This minus 10 got from left as 9. Remember this. So now it's time to go to the right. At the moment I go to right, I have a 20. Correct? So on 20, again, I'll go to the left and on to the right. But before that, we'll go to the left. On 15, on the left, I get a null. So this returns a 0 on the right. That is left sum and right sum. So again, apply the formula left sum plus right sum. That's 0 plus node dot val 15. So maximum gets updated to 15. Perfect. So this guy returns a 15. Why? Because node dot val is 15 plus max of left, max of right is 0. It returns a 15. Now it goes to the right. The moment it goes to right, I have a 7, correct? Again, 7 will do the same task, goes to the left, goes to the right, both has null, so this will return a 0, this will return a 0. Again, left sum returns 0, right sum returns 0. So this 7 will consider it over here, so it will be 0 plus 0 plus 7. So this is 0 plus 0 plus 7, that is 7. So you have already got a maximum of 15. So this maximum will not be considered via the 7. Via the 7, it will not be considered. Hence, this is going to return. And what will this return? Note.val, that is 7. Max of left, right, that's 0. This is going to return 7. This is going to return 7. Now, understand for this node 20. When you are at the node 20, the left sum is 15, right? The right sum is 7. So I know on the left, the sum is 15. Again, makes sense because the node is 15. On the right, the node is 7. So that's why it is 7. So what I do is left sum. That's 15, plus right sum, that is 7. 15 plus 7, 22, plus the current node 20. If I consider this path, so 15 plus 7 is 22, plus 20 is 42. So I'll update maximum to 42. So what I can say is, this guy, via this, got a 42. Perfect. Now, which is the longest path? Like if you're coming across, if you're trying to take it, which path will you take? If you're standing at minus 10, either you'll take this or you will take this path. So which path will you take? This is decided by this. Current node, which is maximum? 15 or 7? 15. 15 is maximum. So node.val, that's 20, plus max of left, right. So 20 plus 15. This returns a 35 rather. So did you understand what happened? Basically, if you're returning 35, it means from 20, take this path. Rather. Current node, which is maximum, 15 or 7? 15. 15 is maximum. So node.val, that's 20, plus max of left, right. So 20 plus 15. This returns a 35 rather. So did you understand what happened? Basically, if you're returning 35, it means from 20, take this path, not this. So you understood that, right? So you have a 35. Now on minus 10, you know, on the left you have a 9. So that's a 9 plus minus 10 plus a 35, which is apparently something 34. Again, that's not greater than maximum. So again, not to be returned. Again, just imagine there was some other stuff. So we will again return node, and if it to any node, so you know the what current right, just apply to this node. Now a lot of you would be thinking of a test case like this. What will be the maximum path in this test case? Then this will be from here to here, and the logic that I said will not cover this because I said from 15, take this left, take this right, and then like whatever is the left, whatever is the right, add that with 15 to get the maximum via 15 on the umbrella path. So you'll be like, but Shravan, that doesn't work over here. That's gonna work. It's very simple. If from the left over here on 20, if from the left you're getting a minus 30, do not consider a negative path sum. If there's a minus 30, you'll say, I'll never consider this, and instead I'll say I'll return a 0. Similarly, if on the right I'm getting a minus 15, never consider this, instead say I'll take a 0. Because taking a negative path will never give me max path sum. Instead, ignoring those negative paths will give me, like the sum will be automatically maximized. So just make sure you ignore all the negative path sums that are coming from left and that are coming from right. Just ignore them. Once you understand the code, it will be much more clear to you. So as always, the C++ code is on the left and the Java code is on the right. So initially we have the root, right? We have the maximum as int mean. In Java, we have taken array because we know that we cannot take a variable and we cannot pass it as reference. So I've taken an array and I've declared with size 1 and I've stored the answer at the 0th index. Just some smartness, nothing else. After that, I've called this function. I've passed the root and the maximum, and once the maximum is computed, I return the maximum. Now the code is very simple. I have the node, I have the maximum, I do the null check, return 0 left. Over here you can see if this appears to be a negative number, like from the left I get a negative sum, I'll not consider that and I'll return a 0. Similarly from the right, if I get a negative sum, I will return a 0. And at the end, I'll say left plus right. Similarly from the right, if I get a negative number, like from the left I get a negative sum, I'll not consider that and I'll return a 0. Similarly from the right, if I get a negative sum, I will return a 0. And at the end, I'll say left plus right plus node val. And that is how you get the maximum. And then you can easily return node.val plus max of left right to be your max. If you're standing here, you actually knew which was the longest path. Like if this is the longest path, you knew about that because your sum was making sure that you are either taking this or you're either taking this, right? Because you'll always take the maximum. So imagine you always took this. After that, you always took this. And from here, there are two options. You either take this or you either take this. So you'll end up taking this. So at the end, this guy took this, and after this. So ultimately, you got this path. So for guys who are still wondering, why did we take the left sum and right sum? Very, very simple, guys. Agar if you're standing at -10, this is what you will take, definitely. But over here, till here but after that you don't know. Either you have to take the left path or right path. So that is why returning the max of, when you're coming back, 0. So ultimately, Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem same tree or not from the Freaka tree series. So basically you'll be given a couple of trees, that's the tree 1 and the tree 2. So in this tree 1, like is this tree 1 identical to this tree 2? If it is, you return a true, and if it is not, you return a false. So over here we can see that the tree 1 is identical to the tree 2. So what we can say is both are similar trees. But just in case I erase this node and I ask you the same question, are the tree 1 and tree 2 same? It'll be like, no, they are not same. They're not identical. So this is the question. You'll be given a couple of trees and you need to return a true if they're identical, or else you have to return a false. So how do you solve such questions? Very, very simple. You know traversals, right? You can do any traversal that you like to. You can do a pre-order traversal, you can do a in-order traversal, you can do a post-order traversal, you can do any traversal that you know. Okay, and every traversal, like the traversals of both the trees, should be equal. Makes sense? Because if the trees are same, like if the trees are identical, the traversal has to be same. Assume I do the pre-order traversal. So what's the pre-order traversal? If you remember, that's root, left, and right. So root, left, right is what the pre-order traversal is. So what I'll do is I'll be at the root of the tree. Yes, I'll be at the root of the tree of both the trees, and we're going to do the pre-order traversal. Simple. And the first time we have a root, we compared, so they're same. So we will go across to the left. I'll go across to the left. The moment you go across to the left, again it's a root left right. So root gets compared. Go to the left, null. Go to the right, null. Again similarly left and right. Come back. Go to the right. Go to the right. Similar time. Simultaneously we have to move. 3 same. Go to the left. Go to the left simultaneously. 4 same. Come back. Come back simultaneously. Go to the right. Go to the right simultaneously again. 5 same. Come back. Come back. Come back. So if you're going to do a simple pre-order traversal, it could have been any traversal, right? The traversal is going to visit nodes at the same time. Like if this is tree 1, tree 2, the nodes will be visited at the same instance. Hence, you can say that the tree is same. So as usual, you have the C++ code on the left and the Java code on the right. So you're given a couple of trees. The root of the initial, like the first tree is P. The root of the second tree is Q. So we're going to do a simple traversal. First, we're going to check for the values of P and Q. And once that is done, we'll move to the left, like both the guys to the left, and right after that both the guys to the right. And if all the guys are returning true, then it's okay, or else we are going to stop. And this case is going to be very simple. If either of them are null or both of them are null, we're going to check if both of them are null, or like in that case, we're going to return a true or false. Very simple, self-explanatory function. Like there's no need to explain this. So the time complexity. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving the problem same tree or not from the Freaka tree series. So basically you'll be given a couple of trees, that's the tree 1 and the tree 2. So in this, hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be discussing the zigzag traversal from the Freaka tree series. Now what does this traversal means? So in the previous traversal, that is the level order traversal, you saw that the traversal was like 1, 2, 3, then a 4, 5, 6. This is zigzag as the name suggests. So first it'll be 1, then you'll go across like this, that's 3, 2. Then you'll go across like this 4, 5, 6. So that's the traversal, zigzag traversal. Like first like this, then like this, then like this, then like this. So kind of this, this, and if there were any other levels, it'd be like this, then it'd be like this. So that's what a zigzag traversal is all about. So we're going to follow this section is from left. Every time you turn this data structure, it travels in the queue. So always we take, you're going to check for 2's right, that's 5, insert that into the queue, so 2 is done. Next for 3's left, there is nothing, 3's right, there's a, and we'll be returning this as our answer. So what we will do different is, we are seeing one thing, that the first traversal is from left to right, then it's like this, right, from right to left, then again from left to right, then from right to left. So we're going to introduce a flag kind of a variable. Okay, so let's introduce a flag variable which is going to say us if we are moving from left to right or we're moving from right to left. So probably we can keep a flag variable. Initially, let's assign it to be 0 or 1. You can do it as you wish. So let's start the iteration of the queue. So in the iteration of the queue, first time when I check out the queue, there's only one element. So we will take it out. Okay. And now what we will do is, if there is a left, there is. So we will insert it into the queue. If there is a right, there is. We will insert that into the queue. Once I've done that, once I've inserted all the bottom nodes left and right, I will take this guy and I'll insert it in the same order like I took it out. That's 1. The flag is 0. Very important, the flag is 0. So flag 0 says us that the direction is from left to right, and the value 1 says us that the direction is from right to left in our traversal. So we are done with 1. So once you have inserted 1 into your data structure, please make sure you turn the flag to be 1, because you're going to the next iteration of the queue, right? And you'll get the next level nodes. That's 2 and 3. So let's get the next level nodes, 2 and 3. Now, you're going to check for 2's left. That's 4. So kindly insert that into the queue. You're going to check for 2's right. That's 5. Insert that into the queue. So 2 is done. Next for 3's left, there is nothing. 3's right, there's a 6. Insert it. So I can say I've done for 2 and 3. So these elements are also done. Now, since the value of flag is 1, what you will do is, instead of inserting it like 2 and 3, you will make sure they're inserted in the reverse order. That's 3 and 2. That's why I said if flag is 1, it's 1 0 1 0. I have left and right. This 0 indeed, and this 1 to 0. And the Java people can definitely follow their code. That's on the right. They're mostly identical, so you can definitely catch up. So initially we are given the root of the tree, and we declare our data structure, that's result. And if the tree is empty, we're going to return the data structure, which will never have any zigzag traversal. Right after that, I declare the queue, and I initially push the root, right? And we have a flag which is initially marked as true. So basically over here, what I'm done is, true means left to right, and the opposite will mean right to left. That is what I have been doing over here. Right after that, I traverse in the queue. So always we take all the nodes of that level. So let's take all the nodes of that level, and what I do is I run a for loop. Okay, I'm running a for loop on all the nodes of that level, and what I'm doing is I'm basically taking it, popping it out. So if your queue, for an example, has 2 3, I will iterate on 2 and I'll iterate on 3 using this for loop. Got it? Right after that, I check. What I check is left to right true. If that's the case, like this 2 that I'm taking out, I'll put it in the front of my data structure. And after that, I'll put 3 if the flag is true. If it is not, what I've done is I've smartly made sure that 2 will come at back, then 3 will come, right? Depending on this flag, I'll either insert it from the front, or I'll either insert it from the back. Simple enough, right? Simple enough, constructive. And the rest thing remains the same. I insert that into our vector or list, and right after that, I check left and right, and I push it. Once I've done this entire iteration, right, I can always switch on the flags, and I'll keep on the data structure whatever is on the row. That's 3 2, whatever is it, I'll keep on the data structure. Once that is done, I can definitely return my result. So the thing that I did different from the previous level order traversal is this one flag and this, while storing in a array or a vector, whatever you can call it. What I made sure is I either push it from the front or from the back. That is the logical thing that I did in order to get the zigzag order traversal. I'm bringing it forward from like this 2 that I'm been through me over here, all the nodes of that level. And what I'm doing is I'm basically taking it, popping it. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be discussing the boundary traversal of binary tree from the FreeCut tree series. So basically, you'll be given a binary tree, okay, and you have to print the boundary traversal. So as of now, you'll be solving the anti-clockwise boundary traversal. If you understand the anti-clockwise, you can definitely do the clockwise by yourself. So basically, if I take the boundary traversal, first you'll start from 1, right? Then anti-clockwise. So you go to 2, then you go to 3, then you go to 4, that's boundary, right? Then you go to 5, again boundary. Then you go to 6, then you go to 10, then you go to 11, then you go to 9, then you go to 8, then you go to 7. So basically anti-clockwise, right? Anti-clockwise. So I want the anti-clockwise boundary traversal of any given binary tree. So how do you solve such a question? It's very simple. First, you're going to take the left boundary. Since it's an anti-clockwise, left boundary excluding leaves, I can say excluding the leaf nodes. That's what I'm gonna initially take. After that, I'm gonna take the leaf nodes, and after that, I'm going to take the right boundary in the reverse direction, right? And if I follow this method, I think I will get my boundary traversal. First, I'll get the left, then I'll get the leaf, then I'll get the right in the reverse. In the reverse, very important. The right boundary should be in the reverse, and also it should exclude the leaf nodes. So let's first discuss how do you get the left boundary excluding leaf. So let's first discuss how do you get the left boundary excluding leaf nodes. So in order to get the boundary traversal, we definitely have to take a data structure which stores the boundary traversal. So the first thing that you will always do is you will take the root of the tree and you'll put it, because that's a part of the left boundary as well as the right boundary. So in order to avoid any confusion, please make sure you put the whatever is the root of the tree into the data structure. Right after that, you'll start off with the left boundary. Now, how do you start off with the left boundary? Again, very simple. You start from the roots left. So you take on 2. You put that into your data structure. That if there exists a left, you will go. So you'll put it on. And if there exists a left of 3, it doesn't exist. So if there doesn't exist a left, you'll go to the right. Very, very important. If there doesn't exist a left, you'll go to the right. So you'll go to the right and you'll get 4. Next, does there exist a left of 4? Yes, 5. But the moment you see that, it's a leaf node. We see that it's a leaf node, right? 5 is a leaf node because it doesn't have a left, neither does it have a right. So it's a leaf node. And I want the traversal excluding leaf, the left boundary excluding leaf. So can I say I have actually gathered my left boundary excluding leaf? So the left boundary traversal has been completed. Now it's time for the leaf nodes. So in order to get the leaf nodes, we have to do a in order traversal. Yes, you cannot do a level order traversal because I want the leaf nodes from the bottom right. I want from left to right. So if you do a level order, it might happen, let's say the leaf nodes are finishing some level above. Like before this, there is a level where the leaf nodes are finishing. So these guys will come up first if you are doing a level order traversal. That's why it's better you do in order traversal, which is basically root, and then it goes to the left, and then it goes to the right. Okay, so what it will do is whenever you do a in order traversal, first you'll get 5, then you'll get 6, then you'll get 10, and then you'll get 11. In this order, you will get all the leaf nodes if you do an in order traversal. Basically, traverse for all the nodes in the tree and check which nodes are your leaf nodes. And whichever are your leaf nodes, just add them into your data structure. So we are done with that, right? Now it's time for the right boundary on the reverse, excluding the leaf. So let's do that. So for the right boundary, what you'll do is you will start from roots right. So this is where you start off. And since we want in the anti-clockwise, we want this in the reverse direction. So you can use a vector or a stack or whatever you want to use. And you're getting 7, right? Next, go to the right. You're getting 8. Next, does there exist a right? No. So if there doesn't exist a right, very, very important. If there doesn't exist a right, you'll go to the left. So that's 9. Next, does there exist a right? Yes. But this one is your leaf node. And it was clearly mentioned that I have to exclude the leaf. So we will stop because it's a leaf node. We have reached the end. So we'll stop our right boundary traversal over here. Now this is my stack or vector. Like you can take a stack, you can take a vector, whatever you want to take, you can take it. So this we have taken. Right now, take from the right, from the last. First you'll take 9. Then you'll take 8. Take from the last, okay? Then you'll take 7. So what it'll make sure is, this is the entire boundary traversal. And make sure that you took 9, 8, 7. So it's already in the opposite direction, right? Already in the reverse direction. So I can say that I have taken the right boundary in the reverse direction. Hence, I have completed all my 3 steps. So if I summarize these 3 steps, I can say left boundary means left, left, left. And if there doesn't exist a left, then you'll go right. Leaf node means normal in order traversal and checking of node, whichever is the leaf node, you just add it. Right boundary means right, right, right. And whenever there is not a right, you move left and you exclude the leaf, like whichever is the leaf node, you just do not take it. And initially, you always take the root node. That's what the algorithm is in order to figure out the boundary traversal of any given binary tree. So let's check out the code. So as usual, this is the C++ code and this is the Java code. Again, pretty much identical. So you can definitely follow the C++ and you can just have an eye on the Java code just if you feel like. So initially, we declare a vector, the data structure, which is going to store the entire boundary traversal. So I first check if just in case the root is empty. Okay, then we're going to just return an empty data structure. Like if we're not given a binary tree, we return an empty data structure. After that, if the root node is not a leaf, then we're going to add that into our data structure. And after that, the 3 steps: left, leaves, right, as we did, and we return our answer, right? So we will check the left, leaves, and right. So let's check the left boundary. So as I said, left means left, 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 left. And if there is no left, then you move to the right. So initially, I start with roots left. And if it's not a leaf node, then only we will add that into our left boundary, excluding leaf, right? Or else I'll move to the left. And if there doesn't exist a left, then I'll move to the right. Super simple. Left boundary. Right boundary is the exact opposite. We start off with the right, right? And if it's not a leaf, we will add it. And we will move to right, 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 right. And if it is not a right, then I'll take the left. Simple. And this time we'll store this into some data structure temp. And right after this, we will take the reverse. Yes, we'll take the reverse. So right boundary is also done. Right after that, we have add leaves. As I said, it's a simple in order traversal. That's left, right. And whenever you're coming to the root, if it's a leaf node, please add that into your data structure. Correct? So there are 3 steps. I can say the left boundary traversal. So we do not complexity. It took a lot of efforts. So I hope you've understood the entire complexity. So there are 3 steps.